Good morning, or good afternoon in my case. My name is Michael Steele. I'm one of the math teachers at Franklin High School, and I'm here to work through and present to you some strategies as well as just kind of work through and talk through a couple practice problems from your Essential Skills quiz model for the first quarter of Honors Pre-Calculus, which if you're taking Honors Pre-Calculus itself, that takes place in either first quarter or second quarter. If you're taking Accelerated Math 3/Honors Pre-Cal, that would take place in quarter 3. In any event, in this video, I'm going to work through all of the problems from your ESQ model. I believe that consists of 4 problems, one for each of the operations you'll be doing with rational functions, and rational expressions. Rational functions will go either way. But I'm also going to just quickly overview beforehand some of the key strategies so that if you want to pursue sort of some additional practice outside of this model, you can go find that stuff really quickly. So in this particular video, we're going to work on standard number 1 or question number 1 on your ESQ. That is rational arithmetic. So we're going to be adding, subtracting, multiplying, and dividing rational expressions in order to simplify them into a single rational expression. It's a skill that shows up everywhere at the next level in calculus, but also it's just sort of a common skill that dates back all the way to elementary school. You may not have recognized it back then because there were a lot fewer variables, but every time you were dealing with those operations with fractions, you were preparing yourself for these rational expressions, which are a pretty commonly found representation for what you run into out in the world. So without further ado, I'm going to go ahead and dive in first to the overview of some important skills, and then I'll work and talk through each of the problems on your ESQ model. There should be in the video description timestamps for each of those sections if you'd like to skip ahead to one. Otherwise, the ESQ model itself has links that connect you to specifically that portion of each video, like that problems portion in each video. So in any event, you'll be able to navigate through really quickly. Thanks for watching, and like I said before, I hope this will be a helpful tool for you. Let's get started though. So first, I mentioned that I wanted to discuss a couple key ideas just to kind of put them in your head in case you're watching this video chronologically. Maybe you looked at this question on the ESQ model and you felt really intimidated. It looked really out of place for you, like something you didn't remember ever seeing before. Well, this is your opportunity to kind of hear a quick discussion about like what are the big ideas that you're going to be using in this case. So first of all, if I had to point to one skill that usually sort of like clicks into people's head, oh yeah, okay, that's what we're doing, that sort of thing, it would be that first line, which is about common denominators. And in a sense, it's basically the same common denominator work you were doing back in elementary school. When you added something like 1/9 plus 1/12, you may not have done it this exact way, but really you were trying to find the LCM, which is another way of basically saying you're trying to break down the denominators and figure out exactly what each one needs in order to make them the same so you can combine them together. So in this case, if we multiplied, it should be a 4, if we multiplied this one by 4, and on the second one, if we multiplied by 3, we'd get 3 times 3 times 4 in each of those denominators. That's going to be 12 times 3 or 36, which means we can write this exact expression as is, as 4 over 36 plus 3 over 36, and we can get our 7 over 36 final answer. So basically, by finding a common denominator, we're able to turn these two expressions into like terms. We are literally making them like terms, or if you prefer, you could think about it as we're then able to factor out a GCF of 1 over that common denominator. So in other words, if you're trying to get through addition and subtraction in particular, common denominators or seeking a common denominator will do the trick for you almost every time. The second piece, and that's built into really the first skill, but the first skill is so specifically a part of rational expressions, I started there, that would be just using your factoring strategies. That's going to involve your diamond strategy, your trinomial factoring strategy, your hard diamond if you still use that language, your mop function factoring when you've got cubics, sums and differences of cubes, you've got hidden quadratics, you've got all sorts of different expressions, grouping of course. All of those strategies are going to possibly play in here. And I think the examples that we see on the ESQ model have sort of one or so of each. You kind of get to see a good expression of them. But there's a whole question on this ESQ each week that's just focused on factoring itself. So you'll be using kind of in tandem those skills across those two questions. Third, there's just fractional fluency skills. Those are typically the things like when do you find a common denominator versus when do you just multiply. Those are also what do you do when you divide two rational expressions. The old flip the second one and then multiply trick. Like why does that work? How does that work? When do you use that? Like those kinds of skills are really essential here. That's not really a high school or even middle school math skill. It's definitely a later elementary school skill. And it's one that's found you. It's been following you all this time. Every time you thought you'd left it behind, it was lurking in the shadows. And then finally, the last one is sort of a broad one, but I think that it helps sometimes with these problems, and that is just a firm focus on what the goal of the question is. In each of these questions, no matter what the operation or expressions look like, your task is to simplify the rational expression. So in other words, whether you're given multiplication, division, or a combination of all four operations, who knows how evil we could be. It's all about that goal of simplifying. And what simplifying means is that you're going to turn this into just a single rational expression. No matter what you're adding together, or multiplying together, dividing together, your final answer should just be something over something. Like that is what you're pursuing, stuff over another thing. So if you keep that in mind, I think that can kind of help motivate your approach just by kind of reminding you, what is it that I'm trying to accomplish here? So there is where we kind of begin. Those are the 4 skills we're going to be bringing together as we work through all of the problems on the ESQ model. We're going to begin then with the first of those 4 questions on the ESQ model. This one, like all of them, tasks you with simplifying the rational expression, and basically it all comes down to which operation we have. So in this case, you can see it. I mean, it's humongous on my screen. We are dealing with an addition problem. So this is adding 2 rational expressions, which you can think of as being almost equivalent to adding 2 fractions. There's just some variable expressions in here instead. And as I noted on the right side, our strategy for this is going to be to factor both denominators and then achieve a common denominator for each of them. In other words, figure out what the LCM is going to be and then make it so that we have just a single fraction over that shared denominator. Now that might sound more complicated than it actually is, so let's actually dive in here. So first of all, when I say factor, I really do mean we're pretty much focused on the denominator here. Almost all of our attention with addition and subtraction is just denominator work. So I'm going to look at those 2 denominators and try to figure out what I can do to break them apart. And when I do this, I'm going to leave a ton of space. I'm just going to leave a bunch of room. You'll see how I mean, like how much space I mean in just a second. But I'm going to do that because we're going to be filling in missing factors potentially. If one has a 7 and the other one doesn't, we're going to need to put a 7 up and down on that second one to get a common denominator without changing the expression, this value. So therefore, we need room to be able to make those additions as we go through. So I'm going to write it out this way. We have 3 over 5x minus 10, and then we're going to add to that 7 over, notice how big I'm making those fraction bars, by the way, too. I'll even extend that one a little bit, over x squared minus 4. Now, as I said, our first move here is going to be to factor. We want to factor both denominators so we can really see what all the individual pieces are. And we want to prime factor them essentially, although there will be times when you don't have to go all the way down to like the nittiest, grittiest prime factors if you recognize sort of what the LCM is going to be quicker. But for us, I'm going to break this all the way down. So 5x minus 10, I have a 5 in both of those terms. I'm going to factor out a GCF of 5. That's going to leave me an x minus 2. And that's it. There's nothing else we can break apart there. If you're like, wait, what about the 1? Yeah, I mean, technically we can pull lots of 1s out there. Not going to change anything for us, though. So there we go. Now on the right side, like it's not a GCF in this case. This is a difference of squares. We have x squared and 2 squared, which factors into x plus 2, x minus 2. Again, it's called a difference of squares. Now that's all really good stuff. That's great. We now have our denominators factored, but we need to get a common denominator. And right now I see 3 separate factors we're going to have to make sure appear in each of the 2 terms' denominators. I see a 5 on one and an x minus 2. And yeah, there's an x minus 2 here and here, but there's not an x plus 2 and there's not a 5 on each of those 2 opposite expressions. So we need to get them in there. So what are we going to do? Well, exactly what you'd expect. I have a 5 on the left side. I'm going to multiply both sides by 5 on the right side, or I'm going to multiply up and down by 5 on the right side. If you're curious why it is we're doing it on both sides, that's of course to make sure both denominators have a 5 so that they have a, quote, common denominator. If you're trying to figure out why it is I multiply up and down, it's because if you multiply by 5 over 5, you're just multiplying by 1, which means you don't change the value at all. It's, for instance, the same way if I had the number 42 and I decided I wanted to multiply up and down by 10. I mean, this would be a weird, unnecessary thing, but 420 over 10 is the same thing as 42. So while I've expressed it in a new way, I haven't changed its value at all. It's exactly the same way. It's one of those things where if you have like $5 in your pocket, you want to feel a little bit better. It's like going, oh, I have 500 cents. Makes you sound really fancy if you're talking about like a preschool or something. Well, for us, we've got our 5 now on both sides. Good job, us. But we also have that x plus 2 on the right side, so we need an x plus 2 on the left side. So I'm going to multiply up and down by x plus 2 because, well, it's the exact same reason. X plus 2 divided by x plus 2, no matter what its value is, unless of course it's negative 2, there would be an issue there, we're going to end up with having that value be 1. So we haven't changed the expression. So in this case now, notice all three factors of my denominator all have check marks. That means they're all the same. We have the exact same denominator. So what I'm going to do now is I'm going to start to bring this stuff together. Now I'm going to do it in 2 steps. I can totally understand if you do it in 1. I typically do this in 1 step as well. But basically looking up here, I've got 2 new expressions for my fraction. And I'm going to distribute pieces here just so I can condense them afterwards. So 3 times x plus 2 is going to give me 3x plus 6. And all of that is going to be over 5x minus 2, x plus 2. And then for the second one, we have 7 times 5 on top, which is 35. And of course, that's then going to be over 5 times x minus 2 times x plus 2. Now from here, like we're ready to bring this together, of course. We now have the same denominator on both of those terms. So you can almost think about it as like being a GCF. You could think about it as each of these terms being something times 1 over 5 x plus 2 x minus 2. And sorry, I'm not going to fill in all the factors just for simplicity. Plus something times 1 over 5 x plus 2 x minus 2. And then we can treat both of these two as our GCF. And if we pull that GCF out, 1 over 5 times stuff, we're just going to be adding those other 2 pieces together. And that's exactly what we end up doing up here. We're going to factor out the 1 over 5 x minus 2 x plus 2, but instead of writing it as 1 over, I'm just going to write it all over 5 times x minus 2 x plus 2. And then up top, we have 3x plus 6 plus 35. Now that's technically correct. There's nothing wrong about that, but we can clean this up a little bit and make it look a little more presentable. And so I'm going to write that as 3x plus 41. So I'm just combining like terms there. And down below, if you wanted to multiply this out, you could, but it'd be perfectly acceptable, and I would argue probably smart of you to just leave it like so. Like this is nice and correct here. If you did want to multiply this whole thing out, I'm not going to do the actual arithmetic to get you there, but if you're curious, you could write this as 5x squared minus 20 in the denominator. That would be correct as well. Now, if there's anything else here, what else could there potentially be? Like, what else could someone ask you for? I suppose that someone could ask you for what are called restrictions. That's something that's covered in Math 3, so that would be potentially showing up there. Your restrictions would be any values that make your denominator equal 0. So in this case, if you had x equal negative 2 or positive 2, you would have a restriction. So theoretically, there could be an instructor out there that demands that you state the restrictions. So if so, there you go. But that's not something you're asked for explicitly here, so I don't expect you'd be asked to do that on there either. But this is a nice, thorough overview of adding 2 rational expressions. Question number 2 is sort of the same process as question number 1, so I'm not going to go into as deep a depth as I did on the first one. I'll probably dive into it a little bit more quickly. If the technique looks uncomfortable or unfamiliar to you, I'd advise you to watch part 1 of this video. But we're next going to subtract 2 rational expressions. And in fact, if you look at them, you might look at those denominators and go, hey, I think I've seen those before. And the answer is, yeah, if you did the first problem, you've seen them before. But that's okay. We're going to use that strategy again. You might be diving into question 2, so let's just demonstrate this technique. As it says up here, our strategy, our technique for approaching a subtraction or an addition problem is the same. Factor your denominators and then achieve a common denominator so that you can factor it out or get just one of it and then combine like terms in the numerator. So in this case, our first step will be to deal with that factoring. So my strategy and recommendation for that would be to give yourself some space and then write out those factors. So we'll do an x plus 2, x minus 2 for the difference of squares in the first denominator. In the second fraction, we're going to have 2 over, and then a GCF of 5 comes out of 5 times x minus 10, or 5x minus 10 to give us 5 times the quantity x minus 2. But then there is one little thing here that I haven't touched yet, and that is this minus sign. Now you could just leave it in there, although danger can happen, and this is actually one of those situations where danger sort of presents itself. Danger might not be your middle name, but it does show up here in the middle of this particular set of rational expressions. But basically, we're subtracting there. What I'm going to do is I'm going to take a trick from Miss Nakamura, something she taught me back in the day to avoid this issue. I'm going to write this instead as an addition problem, which before you get all upset about the fact that I've changed the problem, I'm going to make this plus a negative 2. So it's almost like I'm just bringing that negative sign into a plus -1 times something, just to make sure that we don't accidentally forget to distribute it in, because anything that creates a common denominator will require us to integrate that negative sign in there. So basically there's my move to adjust for that fact that it was subtraction. There's sort of your one little wrinkle that can help you on a subtraction problem. Next, of course, I need a common denominator. We have some progress made already with the x minus 2's, but we have other factors that haven't been taken care of. One of them is this 5, so I'm going to multiply both sides by 5. Again, I do it up and down so that way I'm multiplying by 5 over 5, which is just 1. It's a way to make sure that we haven't changed the value, just the way it's presenting itself. So we now have a 5 on both of the factors denominator, or both terms denominators. And then lastly, we have x plus 2. I need 1 on the right side, so I'll multiply up and down by x plus 2. And that gets us a complete common denominator. So when we combine these together, and again, I'll do this a little quicker than I did last time, we'll have a single denominator for these two fractions being combined, or these two expressions being combined, of 5 times x minus 2x plus 2. Now in our numerator, though, we've got sort of our own game. We have 4 times 5 is 20, and then we're adding to that the -2 times x plus 2. So we need to distribute that -2 in. And this is really where that minus sign being already attached to the 2 is helpful. We're not going to forget to distribute that negative sign to the positive 2 at the end because it's attached with the scalar we're multiplying in. So it's really good stuff. Minus 2 times x is going to be -2x. And then -2 times 2 is -4. And now combining all this stuff together, we're going to get a pretty nice little piece here. I like to write it in descending order. This will be -2x plus 16. Divided by 5 times x minus 2 times x plus 2. And while the previous row would be correct as well, I'd say this is the first sort of expected answer that I would anticipate people running into and presenting on their ESQ. So there is our difference. The subtraction of these two rational expressions yields this. Now, having said that, that's not the only way you could write this. If you watched video 1, or problem number 1's video, then you might remember that you could distribute that denominator in. There's nothing stopping you from doing that, in which case you could write this as 5x squared minus 20. Like, this would be an acceptable version of that answer. That's just multiplying out and distributing the denominator, the one that we have factored. You don't have to have it factored. But there is, of course, one other way you could handle this, and that is you could GCF out something from the numerator. You could write this as -2 times x minus 8, and then have it over either of those denominators. I would anticipate, since, if you factored the numerator, you probably factored the denominator. I don't, purport to know anything about your life, but I would guess if you were going that far, you'd probably go this far as well. But that would be an acceptable expression as well. So there is the strategy and the work done for problems 1 and 2 on this ESQ question, this first ESQ question even. Problem number 3 then moves us away from addition and subtraction and jumps things up a level of, arithmetic intensity. We're now going to be multiplying. And now, while I said it increases the arithmetic intensity, making up phrases here to sound fancy, multiplying two rational expressions is actually a lot easier and a little bit quicker than adding or subtracting them. In fact, there's no more need for a common denominator here. We're just multiplying straight across. So our real strategy is just factoring. Once we've done that, we can crunch everything together into a single rational expression right off the bat. We can honestly do that from the beginning if we so desire, and then just divide out anything that's in common with both the numerator and denominator. So in a sense, multiplication is typically the cleanest, fastest, and most efficient of the techniques, but I think it becomes challenging when you get it confused potentially with addition and subtraction, which do involve a little bit more mathematical labor. So in this case, we've got 2x minus 5 over x minus 3, and that's being multiplied times a far crunchier rational expression, x squared minus 9 over 2x squared minus 3x minus 5. And this is our first opportunity to see some real strong factoring techniques kind of show up and get into play. So to start things off, since 2x minus 5 and x minus 3, neither one features a GCF, neither one's factorable in any sort of meaningful sense, I'm just going to leave them both exactly as is, and I'm going to focus my attention on the second rational expression here. We have that x squared minus 9 over that 2x squared trinomial in the denominator. I'm going to use two different colors here as we go in. And I'm going to use an appropriate factoring technique for each of these. And I'm going to start in the numerator because that's a technique we've seen before. That numerator is going to use the difference of squares technique. We used it already in this video. I think technically we've used it twice already. But basically you can tell that difference of squares will be in here. That's something that gets introduced really early in your factoring times, your factoring experiences. X squared and 3 squared are being subtracted. That's going to factor into x plus 3 times x minus 3. And that difference of squares technique, if you don't recognize it, basically says if you have a squared minus b squared, that's going to equal the product a plus b times a minus b. So there we go. And hey, if you're outside during the summer, don't get stung by AB. You're not laughing. That's fine. In our denominator then, we have 2x squared minus 3x minus 5. This one, by virtue of being a trinomial, although we don't know for sure that it's going to work this way, this one looks like a diamond factoring situation for me, simply because it's a quadratic function or a quadratic expression, and it's got, 3 terms, so that looks like a diamond. But in particular, that 2 out in front makes it what we often call a hard diamond. Sort of a silly name. If you know anything about the hardness qualities of diamonds, they're pretty hard, but we'll go with that here. What that means is we need to attack this in a particular way. So I'm going to write it down here just so we can kind of see it, and we'll remind ourselves what the hard diamond looks like. So our technique for attacking with the hard diamond says we're going to find the two numbers that multiply times the product of the leading coefficient and the constant. So 2 times negative 5, I'll even write it right here, 2 times negative 5 is negative 10. And then they need to add up to that middle number, sign included, so that'll be negative 3. So we're looking for two numbers that multiply to negative 10 and add up to negative 3. Now we're really fortunate in this case. 2 and negative 5, literally 2 and negative 5 add up to negative 3 and multiply to negative 10. So I'm just going to go ahead and put them here, negative 5 and positive 2. And again, I'm going to show you my technique. There's a bunch of techniques out there. If you prefer to use another technique, go for it. There's probably a dozen that are out there that are super viable depending on where you've learned factoring from. For me though, now that I see these two values, that tells me exactly what I can do to basically break this apart. I just split up the negative 3x into negative 5x plus 2x. So I'm going to rewrite what was 2x squared minus 3x minus 5 as 2x squared minus 5x plus 2x minus 5. And again, as we did earlier, as we did when we were finding a common denominator, we're not actually changing the value of anything. We're just changing the way it presents itself to facilitate something like factoring or something like finding a common denominator on the earlier problems. Here it's just to do that. From here I can do two GCFs then. So GCF-wise, as I look, I can see that an x is going to factor out of the GCF of the first two terms. It's going to leave me with a 2x minus 5 left over. On the second pair, I've got nothing but a positive 1. So I'll pull that out, and it'll leave me at 2x minus 5. From here, I now have a GCF of 2x minus 5, so I can pull that out in front, and that leaves me with just an x plus 1 left over. So 2x minus 5, x plus 1, that's our factored version, so I'm going to go ahead and pop that up into my denominator. So now I've broken everything apart, everything is all together, and so while I typically just start slashing, just like, yeah, just start like digging my way through it at that point, let's just, for clarity's sake, let's go ahead and combine this a little more formally. What we're going to do now is, since we're multiplying, we can just combine these together into a single expression. This is 2x minus 5 times x plus 3 times x minus 3 in the numerator. And down below we have x minus 3, we have 2x minus 5, and we have x plus 1. Now with that stuff in place, what's there left to do? Like, what can we do with it? Well, I see there's a 2x minus 5 in both the numerator and denominator, and while there are potential issues if x was equal to, say, 5 halves with that, since it would be 0 over 0, that's not our focal point for right now, so we just divide that out and say, hey, those are the same thing, so they're gone. Likewise, x minus 3 and x minus 3, they're both there as well, so they divide out as well. They make ones. I think that's the language that many schools use in our district. What that does, though, is leave us with one factor in the numerator, one factor in the denominator. The numerator factor is x plus 3, the denominator factor is x plus 1, and while there are ways you will eventually, or have seen, that could break that down further, that's a perfect finishing point for us. That's exactly what we're looking for now. We can see the simple rational expression that was hidden in this massive product. And there we go. That's going to do the trick for us. X plus 3 over x plus 1 is what we've got. Now, if you didn't trust your work, you could always plug in something. I often plug in numbers like 1 or 0 to the original and the last one just to see if they come out the same. But we're doing the correct work here. So I'll leave that to you in case you would like to verify it. But again, multiplication, much simpler. No common denominator here, just some factoring. Like this problem was really only lengthy in any way because of the factoring we had to do. Last, and certainly not least, multiplication's least. Last but not least, we have the division problem. We have x minus 5 over x minus 3 divided by trinomial divided by binomial. So really here, the strategy comes from, or the strategy's uniqueness comes from that division sign, and that's reflected over in our strategy listed on the right side. We are told that our strategy will be to factor and flip, and that flipping is for the second denominator, or the second factor, really, the second rational expression. I'll put it in there as the second fraction. So we are going to flip that second fraction. Now, people always know that that's the case. They're always sure. They're like, oh, yeah, I know I'm supposed to do that. So let's just to kind of remind you why, though, because I think sometimes it can be a little bit trippy to just kind of remember a rule rather than understand why it works. If I tell you I need you to divide 1/5 by 2/3, that can be kind of a weird thing. Well, think of it instead for a second as a division problem. Or as a fraction. This is 1/5 divided by 2/3. And I want to get rid of that fraction in the denominator just because it looks kind of awkward. No judgment, but a little bit of judgment. We are going to get rid of it. Basically, what I would need to do is get rid of the 2 over 3. So I could multiply by the reciprocal to make a 1 down there. But if I multiply by a reciprocal down there, I also have to multiply by a reciprocal up top. And what that does is it gives us a denominator of 6 over 6, which is 1. But up in our numerator, we get 3 times 1 over 2 times 5, which gets us our 3/10, which is exactly what this is equal to. So if you've ever been curious why it is that we take the reciprocal of the second fraction and then multiply, there's your reason why. You're literally seeing its sort of origin story play out in front of you in Kasumnasoke school colors for some reason. So there it is. Just leaving that up there just so you kind of see where it came from. There's your origin story. For us, though, we're going to do the exact same thing. And in fact, I'm going to waste no time. I'm just going to dive in right off the bat and just do that step before I do anything else. So I know it says to factor and flip. I'm going to live on the wild side here. I'm going to flip and then factor. And actually, I'll do that in a different color just so we can make sure to see it. So we'll do the flipping to x squared minus 9 over x squared minus 2x minus 15. Now, if you're wondering why getting to that step is helpful, I think it's just nice because it gets rid of division. Now it's just the same as what we did on the last problem, which, while factoring intensive, wasn't very difficult at all. So now we're in the exact spot we're looking for. We've got a fraction times a fraction. We know we're just going to kind of crunch these together. We've got a little bit of factoring to be done first. So let's do exactly that. Let's do some factoring here. On that numerator on the right side, we're going to use the difference of squares. We've done that enough. I'm not going to beat around the bush, kind of getting us into place. That will become x plus 3 times x minus 3, because that was x squared minus 3 squared. And I shouldn't skip the fact that we do have x minus 5 over x minus 3 here already. And by the way, you can probably already see what's happening here. We've got an x minus 3 that looks like it's going to divide out pretty quickly. It's always good. On the other hand, let's do it in green, what the heck. We've got this second one, this trinomial here, x squared minus 2x minus 15. And that looks like a classic diamond factoring, especially because there's a 1 in front. We don't have to do the full factorization process, although it would definitely work as well. So for us, if we're trying to break apart x squared minus 2x minus 15, if you can't do that quite in your head, we're looking for what two numbers multiply to negative 15 and add up to negative 2. And as you think about factor pairs for negative 15, I'm thinking you're going to arrive at 3 and 5, and then quickly see that if the 5 is negative, this product will be negative, but its sum will be negative as well. So I'm going to go ahead and put this in as negative 3, or negative 5 and positive 3, which if you did want to do the full factoring, you could do as x squared minus 5x plus 3x minus 15. But in any event, when you put that all together, you're going to get x minus 5 times x plus 3. So there is everything completely factored. And I mean, technically, that's good. That's correct. Like, that's good stuff. But of course, we want to get this into a single fraction, a singular fraction. So the question is, what's going to be left over when we bring it all together? Well, looking at these pieces, and again, we can essentially just turn this into a single fraction right from there. I've got now x minus 5 and x minus 3 in the numerator and denominator respectively. So what divides out? Well, x minus 5 and x minus 5 divide out quickly. X minus 3 and x minus 3 do go out as well. We talked about that before. And then, whoa, well, look at that. X plus 3 and x plus 3 divide out as well. That leaves us with nothing. Nothing is remaining. So oftentimes you'll see students immediately go, my answer is 0. That's wrong. Don't do that. I had to before I let you just like stop the video, like, yeah, it's 0. I'm going to stop the video. It's not 0. When we do that, we've divided a bunch of stuff together. Imagine, for instance, that these weren't x minus 5s and x plus 3s, but you had like 2 times 3 times 7 divided by 2 times 3 times 7. Well, what is 2 times 3 times 7 divided by 2 times 3 times 7? Well, that's the same thing as 42 over 42, which of course equals 1. That's exactly what we have left over here. So while I left a lot of space, we've essentially calculated 1 divided by 1, which is equal to 1. So this is actually just equal to 1. So for all that division work, it turns out the answer was 1, which is so clean and simple, I would say that truly we won. I don't have my laugh button here. Oh, well. But in any event, that's going to conclude our video. That's going to finish up the fourth problem. So as a reminder, what we did in this video is we talked briefly about some common strategies that are helpful when you're attacking this question on the ESQ. We did 4 problems, an addition problem and a subtraction problem first, both focused on factoring to get a common denominator so we can combine them together nicely. And then second, we did our multiplication and division pair, which involved the same strategies, factoring basically, but no common denominators anymore. The only real wrinkle was that you did have to take the reciprocal of the second fraction and then multiply it from there. And in the event though, I hope this was a helpful video. I'm going in like extreme depth here. I want this video to be a helpful resource to help you kind of fill in the gaps in case you have any as you approach this ESQ. This is a thing that goes into your grade pretty frequently if the last few years are any indication. So you want to get ahead of it, and I'm hoping some real meaningful and purposeful, intense instruction will help you get there. So in any event, once again, I'm Mr. Steele. Thank you for watching, and have a good rest of your day. I'd say have a good rest of your summer, but that's just me. You're probably watching this during school. Otherwise, that's weird that you're stalking videos on a math teacher's channel in the middle of the summer. But hey, you be you. See you later.